the second part of the topic, the deviation of gases from ideal behavior and compressibility factor. Compressibility factor Z. So, for the ideal gas equation or kinetic gas equation PV equal to nRT or PV equal to 1 by 3 mc square, the different equations, the different gas laws, Boyle's law, Charles' law, Avogadro's law, all the gas laws what we have studied, in reality is found that no gas will follow all these equations and laws under all conditions. No gas is found to follow these laws or these equations under all conditions of temperature and pressure. It is found that some gases will follow at some particular temperature and pressure only this, but in all definitely not under all conditions. That means, the Boyle's law, Charles' law, Avogadro's law, or in general all the gas laws and the gas equation are followed by the different gases only under different sets of only at certain conditions of temperature and pressure, but not at all temperatures and pressures. Means gases do not behave as ideal gas under all conditions. Practically it is observed that no gas is found to follow the gas laws or behave according to ideal gas equation under all conditions. A gas may behave as an ideal gas only at certain temperature and pressure. That means, no gas is ideal gas. No gas is ideal gas. That means, for none of the gases what we have, what we know, either it is hydrogen, helium, neon, argon, krypton, carbon dioxide, sulfur dioxide, HCl, ammonia, any gas you take, every gas may behave as an ideal gas only at certain temperature and pressure, but not at all temperatures and pressures. That means, no gas is an ideal gas. No gas is an ideal gas under all conditions. That means, no gas will follow all these gas laws under all conditions. So, any temperature and pressure for a gas, you can't take the equation of PV equal to nRT. You can't take the equation PV equal to 1 by 3 mc square, because no gas is following this gas laws under all conditions, only at certain particular condition. Then what condition? Generally, a gas may behave as an ideal gas a gas is an ideal gas only at high temperature and low pressure. Here low does not mean very low, even moderate pressure. High temperature and low pressure or moderate temperatures are the favorable conditions for a gas to behave as an ideal gas, right. So, no gas is found to follow all the gas laws under all conditions. So, the meaning is basically that all gases are deviating from ideal behavior. Again, in this deviation, the deviation may be positive deviation or negative deviation. That means either PV is greater than nRT or PV is less than nRT. If PV is equal to nRT, that is ideal gas. But what we are saying is, no gas is following that PV equal to nRT under all conditions. So, in case of certain gases at certain pressure and temperature, PV is less than nRT. For some gases at some condition, PV is greater than nRT, either less than nRT or greater than nRT. That means either it is positive deviation or negative deviation. If PV is greater than nRT, then we call it as positive deviation, this is negative deviation. Certain gases will exhibit positive deviation, certain gases will exhibit negative deviation, certain gases will exhibit positive deviation under certain conditions, negative deviation under certain other conditions. Then which gases will exhibit positive deviation, which gases will exhibit negative deviation, under what conditions is now what we have to discuss. For that to explain, there is something called compressibility factor that is introduced. What is this compressibility factor? Compressibility factor means, compressibility factor in fact is nothing but the ability of gas molecule to undergo compression. Again I repeat, compressibility factor is nothing but the ability of gas molecules to undergo compression. If a gas is allowed to compress, what will happen? When a gas is allowed to compress, suppose you have a gas, here you are having a gas molecule, here you are having different gas molecules. Now if the gas is compressed with the help of a piston, if you compress it, what will happen? At high pressure there is every, as the compression is increasing, there is every possibility that the gas may convert into liquid, undergo compression, gas may liquefy. So this compressibility factor, which is nothing but the ability of gas molecules to undergo compression. The other way, what also we can say is, compressibility factor is a measure of this compressibility factor. Compressibility factor Z is a measure of liquefaction of gases. What is this compressibility factor? How does it varies? For different gases, what is the value of Z at what condition? That with the help of a particular kind of a graph that is drawn for Z versus P, compressibility factor against pressure, graphs have been drawn for different gases. From those graphs, the gases have been classified, that gases exhibiting ideal behavior, non-ideal behavior with positive deviation, non-ideal behavior with negative deviation. That is compressibility graphs, and from the nature of the graph we could explain the compressibility factor, ability of gases to undergo liquefaction, the extent of deviation, the magnitude of deviation of gases from ideal behavior, right. That is what in the graph we are going to look at it. Now compressibility factor Z is equal to PV by nRT. If Z equal to 1, the gas is ideal gas, because Z equal to 1 means PV equal to nRT. Z less than 1, non-ideal gas with negative deviation. Z greater than 1 is non-ideal gas with positive deviation, right. The graph is drawn for different gases. When the graph is drawn for Z versus pressure, at any pressure if Z is equal to 1, any pressure for a gas if Z is equal to 1, then the gas we can say is perfectly ideal gas. But as already we told, no gas is perfectly ideal under all conditions. Certain gases are found to exhibit positive deviation at all pressures. Some gases, these two gases are nothing but the hydrogen and helium gases. Hydrogen and helium, these are the hydrogen graph that is drawn for hydrogen and helium. Then for other gases, nitrogen, oxygen, carbon dioxide, sulfur dioxide. For different gases when it is drawn, what it is observed is hydrogen and helium, hydrogen, helium. They are the gases which are exhibiting positive deviation above this. From very low pressure, as the pressure is increasing, they are showing positive deviation. That means hydrogen and helium gases are exhibiting positive deviation at all pressures. At all pressures they are exhibiting only positive deviation, right. Now, when you come to the other gases, nitrogen, oxygen, carbon dioxide, sulfur dioxide, methane, ammonia, all these gases if you take, they are found to exhibit negative deviation at low pressure and positive deviation at high pressure. So, for example, if you look at it, nitrogen, with increase in pressure initially the extent of deviation is decreasing, means it is undergoing negative, reaching certain minimum, and after that increase in pressure is increasing its deviation, it is crossing from negative deviation to ideal behavior, from ideal behavior to positive deviation. So, basically the point is that hydrogen and helium exhibit only positive deviation at all pressures, that is Z greater than 1. Then other gases like nitrogen, oxygen, methane, ammonia, carbon dioxide, sulfur dioxide, all gases, they exhibit negative deviation at low pressure, positive deviation at high pressure. So, as the P is increasing, initially deviation is decreasing, reaches minimum, and then it increases. Now, here one more thing is, as of course this is Z equal to 1, this is Z greater than 1 and this is Z less than 1. Z greater than 1 means already we told PV is greater than nRT, PV is less than nRT. The other way around also what we can say about the deviation says, if Z is equal to 1, then molar volume is 22.4 liters. But here molar volume is greater than 22.4 liters. This is another very important point. For gases exhibiting positive deviation or for a gas in a condition where Z is greater than 1, PV is greater than nRT, or the meaning is the molar volume of the gas is greater than 22.4 liters. Molar volume of gas is more than 22.4 liters. Z less than 1 means negative deviation. The gas which is exhibiting a negative deviation means its molar volume is less than 22.4 liters, right. For a gas with positive deviation, molar volume is greater than 22.4. For a gas with negative deviation, molar volume is less than 22.4, and for a gas with ideal behavior, Z equal to 1, PV equal to nRT, molar volume is 22.4 liters. This is the extent of deviations. From this graph, what we can understand is certain gases are exhibiting positive deviation, certain gases are exhibiting negative deviation at low pressure and positive deviation at high pressure. What is the reason for this deviation? And which kind of gases are exhibiting positive and which kind of gases are negative, under what conditions? Now it is very necessary, it is now to explain all this. So here the explanation what we can give is that the gases with very low molecular weights, small molecular sizes, where the attractive forces means intermolecular attractions, where the intermolecular attractions are least or negligible, right, they are the ones which are exhibiting positive deviation. As you know, hydrogen and helium, they are being very small in size, they are very small, they are the smallest molecules, atoms among all other gases. The gases with very small molecular size, obviously the meaning is the attractive force will be very less or negligible. They are the ones that they will exhibit positive deviation, but the other gases with increase in molecular size like carbon dioxide and all, if you take, they will exhibit negative deviation up to certain pressure and positive deviation after that. This is what, so from that, as again you can see nitrogen, oxygen, carbon dioxide, sulfur dioxide, with increase in molecular size or molecular weight, the extent of deviation is decreasing initially and then of course is increasing. That is because with increase in molecular size, intermolecular attractions also will increase. So the gases where intermolecular attractions are considerable, where intermolecular attractions cannot be neglected, the gases where intermolecular attractions cannot be neglected, they are the ones that are showing maximum extent of deviation. But if you look at it to the postulates of kinetic theory of gases, where we wrote intermolecular attractions are completely negligible, but in reality it is not. You cannot neglect intermolecular attractions. So in the kinetic theory of gases, where we assume that intermolecular attractions are negligible and we derived the equations, are not holding good in these cases, because in these cases intermolecular attractions we cannot neglect. If we can neglect intermolecular attractions, obviously that gas equation PV equal to 1 by 3 mNc square will hold good. But intermolecular attractions cannot be neglected in these cases, as increase in molecular size is increasing intermolecular attraction. That is the reason they are showing the negative deviation. And another thing is that from this graph, what we can say is that those gases with Z greater than 1, because the molar volume is 22.4 liters, volume is very high, molar volume is greater than 22.4 liters, that means it is difficult to decrease their volume. What do you mean by difficult to decrease in volume? The meaning is that it is difficult to compress them, it is difficult to liquefy them. That is the reason you must have seen, you must be knowing that, you have a knowledge that it is very difficult to get liquid helium, it is very difficult to get liquid hydrogen, but easy liquid carbon dioxide, liquid ammonia, easily we can get. I mean, gases can be liquefied. So the other way around is, what we can put it as, those gases which cannot be liquefied, the gases under which they cannot be liquefied easily, those gases which exhibit positive deviation cannot be liquefied easily, or the other way around, the gases which cannot be liquefied, they only will show positive deviation, and these gases under these conditions can be liquefied easily. Those gases that are showing negative deviation, they can be liquefied very easily. So compressibility factor, liquefaction and deviations, volumes, these are all one is related to the other. Those gases which will show ideal behavior intermolecular attractions are negligible, but those gases which show negative deviation intermolecular attractions cannot be neglected, and they are the gases which can be easily liquefiable, and they are the gases where intermolecular attractions are cannot be neglected, right. Now, taking this fact into consideration without neglecting intermolecular attractions, with neglecting intermolecular attractions, the equation is PV is equal to 1 by 3 mnc square, where we can explain the behavior of ideal gases without neglecting intermolecular attractions. That means, by considering the intermolecular attractions, what is the equation that we have to derive, how we have to explain it, what factor, what modifications we have to do in the ideal gas equation, so that it can be applicable to all gases under all conditions. That modification, that necessary correction is made by van der Waal. After making necessary correction into that ideal gas equation PV is equal to nRT, another equation is derived by van der Waal, that is what we call van der Waals equation. Using that van der Waals equation, we can explain all these deviations. So, now what we have to say is, what is van der Waals equation, what is the theory behind it, what are the corrections that are made, and with the help of those corrections, how do we explain the deviations is now what we have to look at it.